Let's welcome the next speaker. It's
Yeah. Thank you for the introduction. I'm Zihe Gao. The work I'm presenting today, which is reconfigurable two-dimensional coherent laser array with non-Hermitian gauge fields. So this work was done when I was a postdoc in Professor Liang Feng's group at Penn. This is also in collaboration with Bikash Media at IISER and Professor Li Ge at CUNY. So I recently joined Auburn University. So the outline of my presentation is I'll first give a little background on laser array and why we want to synchronize them, and why surprising multimode operation is challenging or why it's useful. Then I'll introduce the main idea of this paper, which is how to suppress multimode operation using non-Hermitian skin effect. We think that's a new way to promote single mode lasing or coherent laser array. I'll probably give a very brief introduction of theory, especially related to the non-Hermitian topology and robustness. Some of them the previous speaker has introduced. Then of course, we'll look at our experimental system, which is this one. So it's a laser array with reconfigurable asymmetric coupling, and we experimentally demonstrated a synchronized 3x3 laser array. The motivation underneath this research is to synchronize a laser array so we can have high brightness source. A single laser can consider it as a resonator, but it has limited power. You can pump it harder and harder, but eventually saturates. Output power, eventually cannot go infinitely high. State-of-the-art single-mode semiconductor laser is limited to about 100 milliwatt per mode. If you want to actually increase the intensity or power, of course you can use many lasers, but although you increase the intensity, the brightness, often defined as the power in a single optical mode, doesn't really increase. To increase the brightness, you have to synchronize laser arrays. The other way to look at it is if you have a synchronized laser array, you can make them have construct interference, then your intensity actually scales with n squared. N is the number of lasers. This has been proposed for 3 decades, but so far there's no mature technology to do this, because phase synchronization between these actually nonlinear systems is actually very hard. Or we can say suppress the multimode operation is hard. Synchronization in here just means we want them to laze in a single normal mode or supermode. Okay, so previously people have tried all kinds of ways to promote single mode, single supermode lasing. In short, I'm not going into detail, but in short, they all rely on one principle, which is adding loss to unwanted modes. But it's harder and harder when the array gets bigger. So when you couple many lasers together, they have many supermodes, and spectrally, the mode you want and the mode you don't want become closer and closer to each other. Spatially, it's also very difficult to separate them. So what we propose here is a very different way to do this mode suppression. We call this single mode lasing from non-Hermitian skin effect. We use the fact that when we have non-Hermitian skin effect, all the modes are localized at the boundary. And then we think this completely changes the mode competition in the array and potentially leads to mode suppression. So first, let's look at symmetric coupling. So before 2020, almost all the laser arrays people studied have symmetric coupling. It means when you couple from laser A to laser B, the coupling strength is the same from laser B to laser A. Okay. When you have this kind of system, if you look at, for example, 1/6 laser array here, these are the 6 supermodes. Fundamental mode is the intensity profile, we're not showing the face, but fundamental mode, first higher mode, and the other higher modes. So you can see they have a very diverse spatial profile. The fundamental mode is concentrated at the center. In the other modes, some of them are more concentrated at the edge. So when I pump this array, the fundamental mode may laze first, but it can only use the gain as at the center of the array. So it cannot efficiently use the carriers or gain at the edge. Then eventually there will be gain accumulating here, and eventually you pump it harder and harder, the gain will bring some other modes above lasing threshold. This is multi-mode competition. Then we have multi-mode operation, then we lose the coherence between the individual lasers. So this is also called spatial hole burning. Okay. However, if we look at a system with asymmetric coupling, and here we have the Hermitian skin effect. I'll go into a little more detail later. But what we have is that, as the previous speaker showed, all the modes are localized at the edge, okay? And this creates head-to-head competition. So in the sense that now after one laser is above threshold, it can very efficiently suppress the lasing of the other modes. So this change, we believe, the multi-mode competition and leads to single-mode lasing. Yeah, the work I present today was published last year. There are also some similar principles, proposals. For example, this PRL paper published 2022 called this anomalous single-mode lasing. Slightly different system, but we believe the principle is very similar. Okay, I'll give a very brief glimpse into the theory and non-Hermitian topology, especially robustness. We think the robustness is critical to why experimentally we observe what we do. Because in our experimental system, inevitably we always have fabrication perfection that leads to detuning between lasers. The coupling is not well controlled, things like that. But fortunately, this non-Hermitian skin effect is robust. Non-Hermitian gauged arrays has been studied recently, theoretically and experimentally in optical lattice, of course, and other optical system and mechanically coupled resonators. Some examples are listed here. Well, I want to emphasize one point, which is the topological origin or robustness, right? So this is the same I showed before. This is a 1x6 laser array, and we can see here the modes are localized at the edge. The thing is, we can add random detuning or random onset energy to the resonators, and you can see the array still behaves qualitatively the same, right? We can add completely random phase to the coupling terms, and it still doesn't change the array behavior that much, okay? So this is indication that it has to be topological. And through a series of theoretical papers around 2020, this is one example, theories actually provide a very beautiful theory to understand why this is a topological behavior. So for example, we can write a Hamiltonian like this when I have unidirectional coupling. This is an extreme case of asymmetric coupling. I have a coupling only in one direction. And this is a Hamiltonian. And in short, I think I could skip the details. In short, if you want to understand an open boundary chain and see whether the mode is localized or not, you have to first analyze the periodic boundary system. In the periodic boundary condition system, similar to, again, what the previous speaker showed, if you plot the eigenmodes, eigenenergies along the real part of the eigenvalue or imagined part of eigenvalue, it forms a circle, the periodic boundary condition. Okay, and you can define winding number. Its intensity is constant, nothing to see there. Because of periodic boundary condition, there's no localization. Then you cut open the chain. Now it's open boundary condition. You calculate eigenvalue again. The cool thing here is I can add detuning, and as long as the open boundary condition eigenvalue is within this circle, drawn by the periodic boundary condition, then the mode is localized. Okay, I can add detunings. I can smear this eigenvalue. As long as it's in the circle, then it's localized. I can add a large detuning, kick one mode out of the circle, and you can see for this mode, it's localized at the defect, not at the boundary anymore. So it's a very beautiful theory you can read more about in this paper. Okay, so now let's look at our experimental system. So this is our system. This is a 3x3 laser array. So we have three, these are the lasers. The ring cavity supports whispering gallery modes. And the waveguides here, the spiral waveguides, just to connect them, introduce the coupling between them. I make them into spiral just so the device is compact. You can use straight waveguides. This device is going to be larger, but it's the same. And each resonator supports two degenerate modes. So one is counterclockwise, one is clockwise. We also call them pseudo-spins. If you look at this pseudo-spin, when it couples from laser 1 to laser 2, it goes through the upper spiral. When it comes back from 2 to 1, it goes through the lower spiral. So if I only pump the upper spiral and leave the lower spiral to be lossy, so this is 3-5 semiconductor, I pump them, they have amplification. If I don't pump, they are lossy. Then I actually introduced asymmetric coupling. So stronger coupling from 1 to 2, but negligible coupling from 2 to 1. If I look at the, oh, okay, I'm running out of time quickly. Yeah. So if I look at the opposite pseudo spin, it has opposite asymmetric coupling. So, well, if you look at each pseudo spin is non-reciprocal, the total system is reciprocal, of course, because we have nothing to break the time reversal symmetry. Mathematically, this asymmetric coupling is equivalent to imaginary gauge potential. It's connected to robust transport from previous studies. This is just showing that the scatters allow us to detect each pseudo spin individually by doing polarization filtering. Okay. In short, this is what we see. Okay. The experimental result is easy to understand. We can reconfigure, by controlling which arms we pump, we can reconfigure the asymmetric coupling. We can make the optical mode to focus equally on the 4 corner. We can make it focus at 1 corner. Throughout the process, the lasers are synchronized, shown by the interference fringes here. So we have a coherent laser array. We turn it into symmetric coupling, we lose the coherence. So this shows that asymmetric coupling or skin effect is indeed the mechanism for for the array to synchronize. Okay, just a conclusion. Well, in short, this is a reconfigurable platform. We think with vast possibility to show, to promote non-Hermitian topology and the linear system. It's also useful as just a technology for high brightness array. With that, yeah, this is the team that made it happen. And thank you for your attention.
Good morning, everyone. So my name is Hamid from Texas, Rio Grande Valley. So I'm talking about the transport effects non-Hermitian topological model. So indeed, in this study, I tried to make a connection between two aspects of non-Hermitian models. In one side, we have some phenomena such as unidirectional reflection in p-symmetric model. And in the other part, recently, we observed some interesting phenomena such as non-Hermitian skin effect, which already mentioned in previous talks. But just to summarize that in this phenomena, the bulk states become localized at the edge of the finite system. So this has happened for the open boundary condition. So I try to make a link that, okay, what's the relation, for example, between the reflectionless of the system and, for example, non-Hermitian skin effect? To show it, so I start with the well-known topological model, SSH model. The Hamiltonian is given by this equation, the Schrödinger equation. So, and I suppose that I connect this lattice to leads from both sides. And also I consider the Hermitian leads. So the leads is kind of the Hermitian version of the lattice. And here I consider the very general one-dimensional lattice, so with asymmetric coupling, so and also on-site potential, it can be complex or real. So the method that I'm using to make this connection is based on the transfer matrix. So we know the transfer matrix in the continuous model, but we can also introduce a transfer matrix for lattice. So here's the equation of the transfer matrix for the unit cell, and then you can find the transfer matrix of the whole system by just making the product of different transfer matrix. But we can also consider the transfer matrix in the propagating state. So this curly M is showing the transfer matrix in the propagating state, in which it's relate the propagating wave at the left lead to the propagating wave at the right. So we need it because we can characterize the different phenomena, different transport phenomena by using this transfer matrix in the propagating state. Okay, if I skip some details, so at the end I end up with this table. So in the first column, so you can see different boundary condition or different transport properties through the system. So let's call it as different boundary condition. So in the second column, so you can find this condition in terms of the component of the transfer matrix. So indeed, for example, if you want to make the system reflectionless, then you can solve these two implicit equations coming from the transfer matrix. So these two implicit equations are the function of the energy of the system, and then you can find the corresponding energy in which you have the reflectionless system. Also, you can use the transfer matrix method for finding this, the spectrum of the system in open boundary conditions. So if you just solve this equation, so at the end you get some discrete complex value that we know for non-Hermitian system. So this is the schematic of the transport properties of the system. For example, you can have CPA, which is the time reversal version of the lasing. You can have reflectionless, transparency. You can combine reflection and transparency and get the invisibility. Okay, let's, if I just consider this, the simple model, which the gain and loss and also asymmetric coupling, and this is the transfer matrix for this model. I have two parameters in this matrix. So D, which is the determinant of the matrix and kind of define the non-reciprocity, and kappa is the topological characteristic. For example, you can have two isolated topological edge for kappa less than 1, and also for KD less than 1. So the state with energy E1 is just localized at the left. So this is coming from the non-Hermitian skin effect. And also we have some Bark 0 modes with the energy 0 if we can if we imply this condition. Okay, if I solve the problem for the reflectionless, which comes by applying these two, by just finding the solution of these two implicit equations, so then I can find this equation, and this equation, I just divided this equation in two parts. So one part coming from the Chebyshev polynomial, so indeed the solution are the Chebyshev nodes. So this is what I call this as a global mechanism. And the second part coming from this factor is just a local mechanism. So if I want to summarize the result, is that from the global mechanism, we can see that the reflectionless is it doesn't depend on the topological phase of the system. So indeed it is independent of the existence of the edge state. But more interesting is that from the local mechanism, so you can see or you can find that, for example, the system can only be made reflectionless from the left. So the reflectionless from the left means there is no reflected wave from the left, just in the non-topological phase. But we cannot make it reflectionless from the right in the non-topological phase. So this is one kind of the condition for the reflection transport and its connection to the topological phase. So we can study the invisibility. For the invisibility, I found that this condition coincides exactly with the skin effect phase transition. So the skin effect phase transition can be given in the, can be shown in this phase diagram. So indeed, by this transition, the two edge states localizes from left going to the right. And also we can make the system's coherent perfect absorber. And again, CPA is irrespective of the topological phase. But what is interesting in this discrete system that we can simultaneously make the system CPA and also the transparent. Okay, so, but as I mentioned, that was very simple and one-dimensional model. So we can extend or we can generalize this study to the model which is more complicated. So indeed it can have some internal degree of freedom, and also we can have such a complicated connection between sides. So you can follow the mathematical method to find the transfer matrix. So the transfer matrix are more complicated, but there's a recipe for finding the transfer matrix. And then you can again characterize the different boundary conditions in terms of the transfer matrix for a very general model. So for example, if you use this method, for example, in the ladder model, so the ladder model is a well-known model in optics. So for example, what you can find interesting here is that, for example, by just tuning a parameter of the system, for example, theta, which appears in couplings, so you can make the system reflectionless from left and from the right in the non-topological phase. So if you remember, so I just showed you that, for example, you couldn't have left reflectionless in the non-topological phase, but here by just playing with the parameter, you can make it reflection from both sides in the non-topological phase. So this is coming from this the general approach that I just introduced. So in the summary, so in these two papers, we introduced a general formalism to establish the transport effect and their connection to the non-Hermitian, non-reciprocal, and topological system. And so this is the perspective of this study. So it is interesting to find the transport effect in some topological photonic models. So they are very complicated than models that I already showed you, but this is the perspective of this book to find the transport effect of such a model. So you can see such an example in this paper. Thank you very much. Yes, actually here, yes, it can. So here I consider the gain and loss. So the I gamma and I gamma prime can represent the gain and loss to the system. Yeah, but the non-Hermitian coming from the non-reciprocity. So I just more focus on them, But the gain and loss is important because I skipped the mathematical detail, but here the difference of gain and loss define in which direction we can make the system reflectionless in topological, non-topological phase. So indeed the difference between gain and loss or difference between on-site potential is important here. Thank you.
Okay. Hi everyone. I'm Vaibhav Gupta from University of Illinois, and I'll be trying to answer this question that you see on the screen at the top. But before answering this question for photonic bands, let's try to get the context right for by answering this question for electronic bands. So consider, for example, this space group 75. The 2D representation of the unit cell looks something like this, where A, B, and C are high symmetry points in the unit cell. For each of these points, for example, point A, you can attach a certain set of orbitals to it, and these orbital configurations, when you attach it to A, are labeled by some special notation that you see on the left side of this table. Now you can repeat this procedure for all the high symmetry points that you see here, and what you get is a set of orbital configurations which are called elementary band representations. Now, because these are orbital configurations, in momentum space, if you take, for example, the first one, they generate a set of bands. And these bands can be labeled by the irreps at these high symmetry points. The collection of these irreps is called the symmetry data associated with this EBR or with this set of bands. Now, the crucial fact for electronic systems is this, that any symmetry data vector for electronic systems can be decomposed in terms of these EBR symmetry data vectors that you get. Now, and in this sense, we say that any electronic band structure can be thought of in terms of an EBR, as in the real space building blocks of any electronic system can be written in terms of EBRs. Now, coming to photonic systems, let me remind you that a photonic crystal is a material in which the refractive index of the media behave in a periodic manner. So here you can see in the image what photonic crystals look like in 3 dimensions. In these systems, the Maxwell equation can be written in this form in terms of an eigenvalue problem. And block theory then dictates that this eigenvalue problem will lead to bands. So these bands are called photonic bands. And here is just a demonstration of how photonic bands look like. I'm just plotting the bands below the first gap here. In this region, near the origin, the solutions of these equations behave asymptotically as plane waves. So the 2 bands that you see here have solutions which look like these transverse modes. But there is also a longitudinal mode which you can introduce in this plane wave approximation. And the directions of these modes you can see here in this diagram. Now, because you have a transversality constraint on the solution of Maxwell equations, all the longitudinal modes in the system become unphysical, especially the 1L mode that you see here. But this introduces a problem, because if in this figure I have removed all the longitudinal modes, all the 1L modes, and because of this, I cannot continue these solutions to the origin in a regular fashion. So this is called a transverse polarization singularity. And because of this singularity, I cannot label the lowest 2 bands with the irreps at the gamma point. Note, however, that the upper bands can still be labeled by the irreps. But because all these bands are connected to each other, the symmetry data for this whole set of bands becomes ill-defined. Now, because we don't have a symmetry data for this set of bands, we cannot proceed further and get an EBR decomposition for this set of bands. So we need to somehow fix the symmetry content at gamma before proceeding. So this was done in this paper a couple of years ago. What we do is we start with our physical set of bands, the T modes that you see here in blue, and we add a bunch of trivial longitudinal modes to the system. And if you focus on this black rectangle here, what we are doing is we are writing the 2 T modes that you see here as a difference between the 2T plus 1L mode and the 1L mode. Now, because we have introduced the longitudinal mode back into the system, the picture starts to look something like this. And now it can be seen from the picture that the modes can be continued all the way to gamma without any irregularity. So because this can be done, the symmetry data for this whole set becomes well defined. And the symmetry data for these added pink longitudinal modes was well defined by construction. So this encourages us to write the blue mode, to write the symmetry data for this blue mode as a difference between 2 trivial symmetry data that you see here. So for any normal symmetry data, we can follow this chain of reasoning to get to the EBR orbital configuration as in the real space picture. Now we have a difference of 2 symmetry data for the photonic bands, and we can follow a similar chain of reasoning to get to the conclusion that this type of symmetry data can be written as a difference of EBR orbital configuration. But this difference structure comes with a subtlety. Consider, for example, an extra set of trivial longitudinal modes that I add to this existing set. Notice that the symmetry data for these blue modes remain unchanged because of this structure. In other words, I can say that the differences of these EBRs get mapped to the symmetry data, but this mapping is a many-to-one mapping. Both these structures are giving me the same symmetry data for BT. So there is a redundancy in this mapping, and we have to somehow get rid of this redundancy. To do this, we need to first identify the sources of the redundancy. So consider, for example, space group 2 with inversion symmetry as the only non-trivial element. If I have an s orbital sitting at a location and I try to move it to a neighboring location, I cannot do so because this final orbital configuration is not inversion symmetric. This process is breaking inversion symmetry. So consider instead the case where I have a p orbital sitting at the same point. These orbitals can now hybridize, and then I can symmetrically move away the orbitals in an inversion symmetric way. And this process is allowed for the system. We denote such a process like this and call it an adiabatic process. So the key feature of adiabatic processes is that any two orbital configurations which are related by an adiabatic process has the same symmetry data. Now consider a more non-trivial example in space group 212. If you start with these set of orbitals at location A and add a bunch of orbitals at location C, then this orbital configuration can be connected all the way through a series of adiabatic processes to this other orbital configuration, where you have a bunch of orbitals at B instead of A. Notice, however, that the orbitals at C are the same. So we can ignore them and write the relationship between these two initial and final configurations like this, and say that these two orbital configurations are stably equivalent. As in, you add a bunch of other orbitals to the system, but still you can connect it through an adiabatic process. So two stably equivalent orbital configurations will also have the same symmetry data vector. So these are the two sources of redundancy that we saw in the mapping that I showed before. And having identified the sources of these redundancies, let us focus on the space group and try to come up with a unique one-to-one map. So for space group 212, these are all the sets of, this is the set of all the adiabatic processes allowed in this group. And you notice that we can come up with these linear combinations of EBR multiplicities, okay, which remain invariant under these adiabatic processes. Moreover, these linear combinations are also the same for two stably equivalent orbital configurations. As in, both the sources of redundancies that I identified in the last slide are gone when you identify this as your starting set. So these special linear combinations are called stable real space invariants, or SRSIs. And as expected, the mapping between them and the symmetry data is one-to-one. So we can focus only on the stable RSIs, and this ensures that we can always map it to a unique symmetry data for any system. Now, because we had some symmetry content at gamma that we repaired by adding longitudinal bands, the inequalities satisfied by this stable RSI is different than the electronic case. For example, here in this figure, I set θ3 equal to 1, and I plot these red lines and these blue lines. These red lines are the inequalities followed by the stable RSIs in the photonic case. These blue lines are the inequalities satisfied by the stable RSIs in the electronic case. And notice that we have these three special points, red, black, and blue. This red point is very interesting because this is a stable RSI which can only be realized in photonic bands. This cannot be realized in electronic bands. So if you look at the blue band now, this is an electronic RSI which cannot be realized in a photonic system. And the black dot here denotes an RSI which can be realized in both types of systems. So because we are interested in photonic bands, we will focus on this set of stable RSIs and try to come up with concrete examples to see how unique this set of bands are. So we start with this stable RSI, and it is easy to see that we can write it in terms of this symmetry data. Notice here that the symmetry content at gamma has this negative sign, and because of this, as I said before, the EBR decomposition is a difference of two EBRs. Okay. Now, because we have a real space picture, we can easily construct a tight banding model to demonstrate the symmetry data. We start with an 8-band model, and we ignore all the negative bands that you see here and take the square root of the spectrum. We get a band structure which exactly looks like that of a photonic structure. And you see that the symmetry data matches the one given at the top. To realize the photonic crystal, which shows the same symmetry data, you just take the unit cell and put a dielectric sphere at the 24e Wyckoff position. And this generates a spectrum like this, which is again shows the same symmetry data as you see at the top. Finally, we also compare some Wilson loops that you see around the origin, these KZ-directed Wilson loops, and plot the 4-band eigenvalues with respect to this azimuthal angle. And you can see that both the tight binding model and the photonic crystal qualitatively agree very well. Okay, with this, I conclude. Thank you for attending my talk, and here is a summary.